So let's do an example that illustrates a bunch of these concepts related to work and how it relates to energy. So this is a problem from the notes that I've selected some parts of for us to do here. So let's say that you take a 1/4 of a kilogram rock and you drop it from rest from a 200-meter high cliff. And we want to know, first of all, what will be the rock speed just before it hits the ground. Now, for this first part, you don't actually have to use any work concepts if you don't want to. There's quite a few ways that you can calculate this, actually. Method number 1, you could use the kinematic equations because there's a constant acceleration here. Because no energy loss also means there's no forces acting on the object except for gravity. The acceleration is gravitational acceleration, and you can find the final velocity that way. Method number 2, since there's no energy loss, you could use conservation of energy to find the final speed. Or method number 3, you could use a work-based method, but that might be getting a little bit ahead of ourselves. We'll get to work in a second. Let's use the conservation of energy method just to practice some energy. All right, so to do a conservation of energy method, the first thing we need to do is identify the initial and final states. So here's my initial state. The object is released from rest at a height 200 meters above the ground. And then my final state is going to be that the rock is about to hit the ground. It hasn't quite touched the ground yet because then the situation is quite different, but it's about to hit the ground and it has an unknown final velocity. Let's call it v. Okay, so there's my initial and final states, and I'm going to set h equals 0 to be ground level. So next thing I would do is write down the potential and kinetic energy for the initial and final state. So for the initial state here, the potential energy is going to be mgh. So that's going to be 1/4 times 9.8 meters per square second times 200 meters. And that is, let me go ahead and crunch the numbers, 0.25 times 9.8 times 200 gives me 490. And that, of course, is joules. And the initial kinetic energy is 0. For the final state, we're going to have final potential energy is 0 because h equals 0. And we're going to have final kinetic energy is half mv squared, not negative because the direction doesn't matter for kinetic energy. So I can plug in the m here. And then finally, you'll set the initial energy equal to the final energy. So we'll have 490 equals 1/2 times 0.25 times v squared. And that's going to give v equals times 2 divide 0.25 and then square root it, 62.6. And it's positive because that's just the speed. If you want the velocity, it would be negative. Okay, so that's kind of the review part. Now, the new stuff. Part B, how much work did gravity do on the rock as it fell? All right, so the first thing I would do is think about this conceptually and decide whether you expect this to be positive or negative, okay? As the rock was falling, was gravity putting energy into the kinetic energy form, or was gravity removing energy from the kinetic energy form? And the answer is gravity was putting energy into the kinetic energy. So I'm anticipating that the work done by gravity should be positive. You can also check that with the force-based viewpoint. The gravitational force here is downward, and the displacement is also downward. So the force and the displacement are in the same direction, which also predicts that you'll get a positive work done. Okay, so I'm expecting a positive answer. Now I need to use some kind of energy change if I'm going to calculate this using the energy-based framework. You could, of course, use the force-based framework here, but I'm going to use an energy-based framework. The quickest way to do this, or the simplest way to do this maybe, is to say that gravity is already being taken into account with a potential energy. So because of that, I can think of this work done as being internal to the system. So I can calculate it as minus delta U. And I've already calculated all my U's over there. So I'm going to have minus the final, minus here the initial, which was 490. So those two minus signs cancel out, and I get that the work done is positive 490. And it is positive as I expected it to be, so that makes sense. So there we go. There's the work done by gravity. So that's part B. Part C, now here's where you can actually maybe do some things with this work and energy-based framework that you couldn't do so easily with some of the previous techniques in the course. In this case, let's say that you sit down, you do this calculation on a piece of paper, you have your expectation that the speed of the rock before it hits the ground is going to be 62.6 meters per second. Now you decide to actually go out, find a 200-meter high cliff, drop a rock from it, measure the speed of the rock before it hits the ground, and you find that this simple calculation isn't quite right. The real speed of the rock before it hit the ground was 55.21 meters per second. So in reality, the rock is going a little bit slower than you expected. But that makes sense because you didn't take friction into account here. We didn't take air friction into account here. The reality is that friction is going to slow down the rock a little bit. So my question then is, how much work was done by friction? How much work was done other than by the gravitational force? Okay. Now, there's a few different ways you might go about doing this part of the problem. First of all, let's do it conceptually. Do we expect the work done by friction to be positive or negative? To answer that question with the energy-based framework, the question you're really asking was friction putting kinetic energy into the rock to speed it up, or was friction taking kinetic energy out of the rock to slow it down? Well, obviously, friction is going to be taking energy out to speed it down. So I'm expecting the work done by friction to be a negative number. Okay, that's my expectation going in. Now, how are we actually going to calculate it? The way I would do it would be this. Let me go back to the left here of my original setup for this question and modify some things. The initial potential energy is fine. There's no change there. The initial kinetic energy is also fine. There's no change there. The final potential energy, that's also fine. There's no change there. But the final kinetic energy, this is now a little bit different because now we know what the final velocity actually is. So let's put in here the observed final speed, which was 55.21. And that gives me a final kinetic energy equal to 0.5 times 0.25 times 55.21 squared. And that gives me a final kinetic energy of 381 joules. Okay, now, this last calculation, this is now not valid anymore because I can't use conservation of energy directly on this anymore because I have to take the work done by friction into account. So what I'll note here is that the total initial energy is 490, and the total final energy is 381. Now, the work done by friction is basically an external effect, which is not being taken into account in this process already. So that means I can calculate the work done by friction as the change in total energy of the system. And if I do that, I'll do 381 is the final, minus 490 is the initial, and I get, what's that, negative 109. I did get a negative number as I expected, and so the work done by friction on the rock is negative 109 joules, meaning that friction actually removed 109 joules from the rock's energy. Okay, that would be one way to do it. Let me show you another way to do it. Let me delete this text up at the top so I make a little bit of room for myself. Let me show you another way you could do part C. You could use work energy theorem. Work energy theorem says that the total work done by all sources has to be equal to the change in kinetic energy. In this problem, the change in kinetic energy is 381 minus 0. So the total work done by all effects acting on the system has to be equal to 381 joule. Now, what are the various effects here which are doing work on the system? And the answer is that we have two things. We have the work done by gravity, and we have the work done by friction. The work done by gravity is the same as it would have been in the other part, because it's negative the change in gravitational potential energy. So the work done by gravity is positive 490 joule. The work done by friction is unknown, but now I know that I have 381 is the total work done, and that has to be equal to 490 plus the work done by friction, and I get the work done by friction is the exact same calculation, negative 109 joule. So that's another way. That's how you would directly use work energy theorem here if you want to kind of have the party line idea that work energy theorem is actually the fundamental idea here. So that's kind of the thought process of how you go about wrapping your head around how work and energy fit together and what are some things that you might use this idea for.